Today I bring you a review on how to consider wind loads in Canopy based on this magazine structural components article called Wind Load Effects on Canopy Systems by Medapati Abhina Reddy from July 2020 and from ASC 716, chapter 30.11, attached canopies on buildings with heights smaller than 60 feet. The design weight from canopies attached for the walls of low-rise buildings are determined by the following equation, that it's P, that is the pressure, it's Q sub H times GCP. As we all know, Q sub H is the velocity pressure, that it's calculated with 0.00256 K sub C times K sub CT times K sub D times K sub E times the square velocity. GCP is the pressure coefficient for attached canopies from figure 30.11 1A and B for contributions for both upper low and lower surface individually and their combined effect on the canopies. So we'll see figure 30.11.8 at the beginning. In here we're seeing the pressures from up and from upper surface and from lower surface, applying as separate load cases. As we can see, the positive is for down. The positive is for downward. I think the lower is the lower surface has positives, and the upper surface has negative. That it's like suction. For pressure, we have 0.8 in the upper surface and in the lower surface. But for the suction section, for the lower surface, we have 0.8 negative. But for the upper surface, we have minus 1.2. So we obtain in the upper surface a bigger suction than the other ones. Then is this figure that is called 30.11/1B, that it's also in ASC 716. And this is analyzing the contributions from upper and lower surface obtaining at the same load case. As we can see, this section is depending on the HE, that it's the mean eave height, and the canopy height interaction. For all pressure loads, we all have the 0.8 that we have before. But for suction loads, I'll make it bigger. For suction loads, depending on the interaction between HC and HE, if it's 0.5, we have 0.6 minus 0.6. If it's between 0.5 and 0.9, we have 0.9. But if it's between 0.9 and 1, we have a GCP value from 1.4. This gives us a lot of suction, bigger than this section. From the article that I mentioned before, we can see that these values that are shown in ASC 716 are for buildings with height of 60 feet or less. The code is yet to include a section for buildings higher than 60 feet. The height of the canopy and the height of the parapet wall, that is the wall that the canopy is attached to, are really important factors for estimating wind pressures. The upper surface pressures on a canopy is a direct downward force on the top of the canopy. This occurs when the wind is obstructed. Imagine that the wind is coming from here, left to right, and it's obstructed by the parapet, by this wall. So it turns into pressure going down. See below from Mr. Red's article, from a relatively typical rectangular building, the key difference between canopies for short building and for high-rise building is that short buildings canopies are often at the near of the roof level. So this will be at this height, near the roof level. So it makes this makes the attached canopy a part of the roof system and has to be designed for roof uplift. But for high-rise buildings, the parapet and wall is much taller, increasing the downward force acting to the canopy. So imagine that the wind is coming from here, gets to the wall and go down. So this load is a lot higher than the other ones, like this one. Lower surface pressures is often combination of, in this case, is combination of uplift, the suction going uplift, and the roof uplift itself. So it's going gets to the wall and go up, and the suction from the roof itself. Now the article says also that many canopy systems in buildings are designed using glass in the canopies. So as we all know, the glass allows very small deflections. So we have to be really careful using using high-rise buildings with glass, because the pressure that we're obtaining is a lot higher than regular pressures on canopies. And that's it. Do you have any questions? Anyone have any questions?
That was great. Thanks, Juan Pablo. Yeah, and just to reinforce what Juan Pablo said, it's funny that the ASC 7 hasn't yet included a section for buildings higher than 60 feet. Manaf has recently done a canopy wind load preliminary work on a building that was like 120 feet higher, and it looks like the pressures for shorter buildings under 60 feet on canopies would end up being higher than canopies put on a building that's a lot higher, closer to like the mid part of the building, if they have like a terrace or like a penthouse area. But I think Juan Pablo, what he was explaining was that for shorter buildings, sometimes canopies are closer to the roof, so you have the higher suction action, more similar to a zone 3 or zone 2 on a roof. Whereas on a taller building, like the image on the right, you have a lot more wall that deflects the wind downward. So the downward pressure tends to be higher for tall buildings than the downward pressure for short buildings, because there's not a surface forcing the wind down.
Yeah, that kind of makes sense. Can you back up a little bit to where you get to the coefficient factors?
Of course.
For the for right in there, it actually looks like, it could be, possible to have 1.4 as a negative pressure coefficient, in combination with a positive underside coefficient of, is that 0.8? So it ends up to be about 2.0 if you add those together, with a positive under the, positive pressure underneath the canopy, and then a negative on top of the canopy. That looks like that would be, is that right? I'm kind of looking at that right?
Yeah, because one is pressure in the canopy and the other is suction in the canopy. So you can combine them. So that's the craze, not the craze, but that could happen. That could be a load case. In this section, we're seeing the combined stuff. So as the figure says, net pressure coefficients on attached canopies considering simultaneous contribution. So I was thinking that 1.4 was the top GCP that you could use, because it's combined.
Oh, they're saying it's already combined. You don't have to figure out the coefficients separately for the suction, and then and separate for the positive pressure for the underside.
Exactly. In the figure 30.8, you have the GCPs from separate load cases. One pushing and the other like just pushing and the other just suction. So this is pressure coefficients on separate surface canopies, but this one is combining both. So the 1.4 is the maximum GCP that you could use.
Okay.
And I think that would apply for canopy structures. A number of people in the office have worked on the Chipotle canopies, that they have a bottom and a top surface. Maybe the cases where you have a top surface independently from a bottom surface is where you have those type of sandwiched canopies, that you have components on the top and components on the bottom that somewhat act independently. But other than that, I think most of the cases we would apply just the combined pressure and suction.
Right. Back up to the previous coefficients Are these individual then? So that you would have to find what the negative uplift is on top of the canopy and then combine that with a positive that is down on the lower surface of the canopy?
I was thinking that you have different load cases. So you imagine that you have the wind coming from up to down. You have this in here. You have a pressure going from there down. Other load case should be from here up. So you'll have suction. You have pressure from going down or going upward. You have different load cases. You're assuming that the pressure is different load cases. One going up and the other going down. Is that our instinct?
Well, I would think that if you had positive wind on that face of the wall, that would create a positive pressure on the underside of the canopy, and then a negative suction on the upper side of the canopy. Is that not correct?
So I think the easiest way to understand it is the 30.11-1B is for the main wind force resisting system of the canopy. So for instance, if we have a steel canopy that they're cladding in ACM, the steel would be designed for the combined load, or the combined coefficient.
That would be figure B.
Yes, and this one, the ACM would be designed independently of that because you're not going to see
whichever surface it's on.
Yes.
Okay.
So a glass canopy, you would use B because you're going to see both.
So I'm just thinking about for the example of the Chipotle and those types of canopies where we actually do have the structural members, that would be in B.
Yes.
So look at that. Yeah, for the main.
But if you're
But the panel,
on the
Yeah,
bottom,
but the panel that's
But the
clad in that
itself,
would be,
you have to refer to that.
Yes.
Okay, got it. Yeah. Good discussions. Very good lesson learned. Thank you, Juan Pablo. Any other questions on that?
For comments?
If we had a building that was a low rise with a parapet and a roof, would you take your HE to be either the parapet or the roof, whichever yielded like a higher external pressure coefficient?
Say that again.
So if you have like that with the parapet right there, the roof is going to be, a couple of feet below that. What would you take your HE to be? Would you be the roof line? Because then you'll get a higher HC over HE.
Yeah.
Yeah, I think so.
As it gets this HC higher, the interaction is higher. You'll get a highest GCP for figure 30B.
Yeah. Notice that, the closer that gets to unity,
Take the most conservative.
the closer that ratio gets to unity, the closer that we resemble an actual roof situation. And hence the higher the negative GCP, hence the higher pressure on suction. So yeah, I would probably use whatever gives you the HE over HE closer to 1.
Yeah, it will be 1.4 in this case.
Yeah.
This is the combined. There's one that is the different load cases. You don't have this interaction.
Yeah.
So Stuart, let me ask you a question that you may have seen in your previous years. Is there a limit to the depth of a canopy before you have to start considering it like an open structure roof? So for instance, like a bank, if that canopy extends out to maybe 4 or 5 bays and it's relatively low to the ground compared to the roof, is that still considered a canopy, or is that now considered an open structure that's attached to a building? How would you look at that?
Excellent questions. All of this is relatively new. This is not, from the past of, they've started to break away, these types of issues and create charts and studies for them and all the other stuff. I think I would probably consider it, if they started moving that thing away from the building, I would almost be tempted to treat it as an open structure, to figure that out.
I had a ASCE PDH thing that kind of talked about some of this stuff. And we've had a few around the office now where it was like, even just not just that, like not just like unique situation. It's something where canopy, but it's ASCE 710, you know, and that's not technically in like some of this canopy stuff isn't even in that. And so what I've been doing is that I got from her who did the PDH was I just run like a few different scenarios. So I'll run like 716, I'll run it as an open structure, I'll rub it and run it connected to the building. Because she was like, and sometimes you just have to do that. You just have to run a few of them and you have to use an engineering judgment of, let's say you run all of them and all the wind pressures are pretty much the same. Like, okay, this is a moot point. Let's say you run all of them and one of them's crazy. You're like, does this really match that scenario or are we somewhere in between? So sometimes that's the best.
I think I did that same PDH and I was more confused after watching that lady than ever before. Because the example she gave was like she gave an example of the Magnolia Farms, that place down in Waco, Texas.
Yeah.
They attached a building to a silo. She
What?
goes, so you have to have on this one, she goes, I would have eight different wind things I'd look at. I'd look at it for a cylindrical tower. I'd look at it for a main building, but since there's like this smaller portion of it, I would consider that a different wind pressure than the main building. I'm like,
Yeah.
this gets so complicated when you do it like that.
That's one of those ones where in the training, I considered, that's never happening to me.
Yeah. I just lean that one piece from it. I was like, oh, just run a bunch of scenarios and see which one kind of applies. But yeah, when she was getting into some of that, I just kind of zoned out.
Yeah. And then she said something that I'm like, I strongly disagree with that. She goes, if your project has a wind load study, that doesn't necessarily mean you have to use the wind load study. So like, she did a project, I'm like, oh, I would not admit what you're admitting out loud. They did a wind load study and like the highest pressure on the side of the building was 45 PSF for the main wind force. Okay. She calculated it by hand and said, oh, it's actually 90, double what the wind study showed. And that's what she used to design everything instead of this very expensive wind load study.
Wow.
I'm like,
I thought you were going to say that she used pressures.
no, she like,
At least she's conservative.
But it's doubling.
Because how she described the other scenarios of where she parts and pieces stuff to get the wind load pressures, this building, which was very much what she was talking about in previous stuff, she goes, well, for this one, because it's so high, I just drew a rectangle around it and treated it as a really wide, high rise. But really the base was wide, but the tower itself was kind of like what we see. It's skinnier. I would not admit that I doubled basically the wind load pressures and potentially cost double the steel and concrete cost.
He's the architect.
I mean, that's a recorded PDH that you can see on the ASC 7 right now.
Is there any reason, similar to what you were saying about you have a project ASC 710, why can't in a condition like that we just use what's newer things that have been developed in 722? Yeah, something like that. Because if something is not included in code and we know that it's been revised to include that, just because it's not in the code doesn't mean that, it doesn't exist now. We have better knowledge of what's
I think
Well, the code is, remember, the title of the code is minimum required loads.
I've had in the past, architects and engineers, that are reviewing argue that they don't have to, do that, and so, that's an argument for a different day, but, usually you have to argue those things like, hey guys, they know more now. Don't you want to, have it done in a right way? Those types of issues that
I think as long as you're not,
Yes.
yeah,
Oh, no, it's
Yeah.
not.
No, we don't have to do
So
that.
we don't, yeah, just ignore
I think as long as you're using the project wind speed. So for instance, there's some areas in the United States that there's a big difference between the design wind speed from 710 to 716 to
it.
722.
Use the
So long as you're using the one in the structurals, the methodology of how you get to the wind speed is, or wind pressure, I should say, is kind of on us.
Yes.
This came up in New York a lot because New York until like, I think last year, they were ADM 2000. They were ASCE 05.
Yeah.
And so it was so old. And then that also referenced ADM like 2005. And so we had the taxi building and the consultant put specifically in the specs used ADM 2015, even though we know, and it said we know New York City building code says use this, but it came so far on open shape buckling. It was like, you can't use ADM 2005 anymore. Luckily, in 2020, New York updated. But yeah, I think
Yeah,
it's
if you get to a point where, yeah, the buckling, oh, it doesn't work, and they say, well, we don't require that in the older version. You're supposed to use the older version. Like that doesn't make any sense. It's not. It has to be in the book and code for it to exist.
Yeah.
It doesn't matter.
I think it's, a lot of the way that engineers will operate and architects operate because they can see it in black and white and they want to have some justification for why they don't have to increase cost or whatever. And so they back up into that.
Does that hold up?
No.
Like, well, okay, it's not the code. You were right. Yeah.
The reason that the code modifies itself are because of studies and failures of the past. So you make that justification that, hey, the code is evolving, because of the failures of the past. Why aren't we doing this? Yeah.
That's how we show value as engineers, not just like following equations, but hey, we're actually trying to make the built environment better.
Yep.
Yeah, absolutely. Very good. Nice job, Juan Pablo.
Thank you, Stuart.